Welcome back to another Recall by Dataiku video. In this video, we're going to talk about some mathematical concepts that are required in machine learning, and then we're going to tie this to a very practical application at scale with Dataiku. So stay tuned. Now, I'm going to be mentioning these mathematical topics in the order I think that it should be learned, starting with mathematical functions for machine learning. Now, mathematical functions essentially map inputs to outputs. So if we write like this little function, we have f, it will produce an output after taking in some input, which is in and out. Now, these mathematical functions are essentially, well, they can be machine learning models themselves. So these machine learning models will learn to take in an input feature, and they'll produce an output which, well, during training it's a label, but during inference it's an actual prediction. A very nice thing about functions is that they also have a visual and graphical property, so you can see how they behave visually. So let's say this is the x-axis, which will be feature, and then the y-axis over here, which is going to be a label. And the interaction between how these features are related to the labels could be simple, like a straight line, or it could be something that's more complex, or anything in between as well. That could be continuous or discontinuous. Now, how these features are related to labels are kind of dictated by the data itself that we use for training models. And we can store this data using, well, the next thing that we're going to be talking about is matrices. To actually show the importance of matrices and matrix operations, let's actually consider a very practical example with machine learning. So I have a model over here in the center, which I'll just call model. And this model is going to help us predict whether or not a flight is going to be delayed. So because it's a model, we said before machine learning models can be interpreted as mathematical functions, and thus they have an input and an output. Now, the inputs to these machine learning models, let's say that one of these features is the percentage of times that the flight has been delayed in the past. And let's say that a second feature is whether the current day is going to be a holiday or not a holiday. Now, these two features are going to be piped into the model, and we want as a prediction, well, whether or not that flight is going to be delayed for departure. Now, the training data for these features and this label can be stored in matrices. So for example, let's just create a matrix over here and say that, like, let's say there was like one example of some Delta flight like 2 weeks ago. The number of past flight delays that it has is 57%. And let's write that as 0.57. And let's say that the day that it had to departure was a Saturday, which was a holiday. So I'm going to represent that as 1. Now, likewise, in the same situation, we could have had, like, let's say another flight. Let's say that it was some American Airlines flight that had the percentage of flight delays was like 31%, in which case we would write 0.31. And the departure day, let's say that it was a Monday, which is a working day. And so this is going to be 0. We're going to put that as 0 for the feature. And so on. Let's say that we have like 10,000 examples or something like that, and we would populate this matrix over here. Now, similarly, what about the data of the actual labels? In this case, well, for the first situation of that Delta flight I talked about, well, this flight was actually delayed. And so let's put it as 1 for, yes, it was delayed. And let's say that the second flight, the American Airlines flight, was not delayed. And so maybe we'll just put it as 0 for not delayed. And we can also, likewise, populate all the some 10,000 flight examples here. And so technically this is a matrix and this is a vector, but vectors in mathematics can be considered as like one-dimensional matrices. But overall, their primary use here is to actually be a facility to store and represent data. Now, vectors, when we pipe it into the model, they're going to be used to train the model. And by the operations that are performed within are kind of like matrix multiplication, or they might be like added together, and multiple operations that go on within this model architecture framework itself. And so learning about matrices and their operations becomes very important, particularly during model training and inference time. Now, the thought of introducing random variables here does kind of sound very random, no pun intended, but random variables is actually a very fundamental concept that helps us relate real events to actual quantifiable numbers. And when we have numbers, we can perform some mathematics on them. And so they are very important. So let's actually walk through this a little more concretely. Now, random variables, mathematically, they are essentially functions. So I'm going to say that let's call this little box here RV. That's for random variables. And these are essentially functions. So they have some input and they also produce some output. And the input to these is some outcome of some event that occurs. Outcome. And what they produce is going to be some quantified number of that outcome. Now, on its own, this definition might be confusing of like where and why it is even useful. So let's actually take a very practical example. So let's say that we're concerned with a specific flight. It's going to be a Delta flight 9471. And let's say that it's the same flight that was corresponding to our first training example over here. So for this flight, I'm going to define a few random variables. I'm going to call it W subscript 1 because this is probably like the first flight that we're looking at, maybe. Then we're going to take a look at another random variable called X1 and then another one called Y1. Now, because they are random variables, they are functions, and they have an input and output. The input is some outcome. So what did we actually see here? Now, let's say that W1 represents the first feature that we wanted for our model, which is the percentage of past flight delays for, well, DL9471. And let's say that, we measure this and we see, oh, there were like 57% of past flight delays. So that's the outcome here that we saw. And because this is the outcome of some real-world experiment that we saw, we can now map this to a number with the random variable. So this would be mapped to a number 0.57. Now, similarly, we'll define another random variable x1, and this is going to represent whether that Delta flight departed on a holiday or not. So we know that, well, that Delta flight departed on a Saturday, which is a holiday. And because it departed on a holiday, the random variable is going to encode this outcome into a number 1 for the affirmative yes. Now, the same thing can be said about this last random variable, y. So y1 is going to be, again, for this specific delta flight, was this delta flight delayed now? And well, yes, we observed that it did leave a little later. So let's write that out. And this is also encoded into 1. Had this not been delayed, then we would have probably said this would be 0. And so I hope you can kind of see what this could be used for here. We are able to now take some real world flight experience and then map it into some number that, well, we can use to perform mathematics. One example or one application of this is to use these numbers, like these numbers in training data. These would be the features and this would be the label. And that's exactly what we do in this matrix and this vector over here, where we're essentially constructed the top row. And similarly like this, we can define random variables for every single one of like the 10,000 flights that we used to train. But there are more applications of random variables. So for now, we saw the outcome of, for example, W1 to be 57%. But this could have very well been like 56% or 55% or 53.7812%. So to understand more about the behavior or the probabilistic nature of flight delays and also of holidays and also of delays in general, then we can also use probability distribution functions. Now, since probability distribution functions are functions, I'm going to draw them out graphically. So here I've drawn 3 graphs where the x-axis is going to be a set of values that a random variable can take, and the y-axis is going to be some representation of probability. And probability distribution functions maps one to the other, where the inputs are the x-axes and the outputs are these y-axes. Now, let's actually look at a few examples based on the case study that we've been seeing so far and discussing so far. But I'm going to start with x1 because it's kind of simple here. So the simple case, x1 represents whether or not this flight departed on a holiday or not. So it can only take in 2 values. So we're going to call them 0 and 1 for not departed on a holiday and departed on a holiday. And let's just assume that a lot of the flights just truly do depart on holidays. So I'm going to put this, let's say it's a slightly big bar, and this is going to be around here. And you're going to see like a 0.6. Whereas with those flights that have not departed on holidays, let's say it's over here, and this is 0.4. Now, similarly, let's do the same for y1, where, again, because this is going to represent whether or not a flight is delayed, it has 2 values. So that's 0, not delayed, and 1, delayed. And let's say that the majority of the flights are just not delayed. So I'm going to put this way up here. This is going to be about, let's say, 0.91. And this one is going to be a bit down here, and it's going to be 0.09. Now let's move on to the random variable w1, which is a little more interesting because it goes from 0 to 1. Like in our examples, we've used an example of 0.57 for 57% of flight delays. But it could have also been like a 56.3287% of flight delays, any arbitrary number in between this. And because it can take on basically an infinite number of values, which can be measured within this range, we call W1 a continuous random variable. And when you graph it out, you can't just draw bars like this. It just doesn't make sense. And so it would turn out to be something like a smooth curve. And let's say that the distribution would look something like this. Now, a cool thing about these probability distribution functions is that we can answer some pretty interesting questions. Like, for example, what is the probability that a flight has been delayed in general, right? Well, we can kind of look at the random variable that represents flight delays, and the probability that a flight is going to be delayed, it's 0.09. Now, this is like 9%. Now, technically, this distribution itself is the label. So it's something that the model doesn't know and it needs to learn on its own. And when it learns on its own a distribution that is as close to this as possible, it can then start making predictions on its own. Now, this is clearly the most interesting thing then that the model is trying to know and trying to learn. And so probability distribution functions become very important in machine learning. In addition to that, in just broader data science and understanding your data in general, I'm sure that just understanding like how flights are delayed or like how many flights would depart on holidays versus on weekdays is also just something very intriguing to know, just as a business goal in general. So I hope the understanding of probability distribution functions becomes more clear. Now, an analog, probably like a sister or brother to probability, is another concept that's super important, and it is likelihood. So likelihood itself is not a probability, it is a value that is proportional to a probability. And it quantifies exactly how well a distribution fits the data. So let's take like a really simple example here. I'm just going to draw a linear regression. We're going to be moving away from the current example because that's kind of a classification, and I want to take this into like a very simple space. So first of all, let's just draw a two-dimensional linear regression. Now the x-axis here is going to be some feature, and the y-axis is going to be some label of interest. And let's say that we observe a bunch of points. I'm just going to draw these as white dots over here. Now here's a question. How do you know if a model is better than another model? Well, for one, let's just draw one model, let's say that we train, and it learns something that looks like this. It's a linear regression, so let's just say that it learns a very simple function that looks like this. And now let's say that we've trained, there's like another model, a parallel model, that it might have learned something that looks like, well, it looks something like this. And then we have a third model that looks, well, like this. How do you tell which is like better than the other ones? Well, this is exactly what likelihood will quantify. So for example, let's say that we take this first model over here because we know that models are mathematical functions, and so we can represent them in this way, just as a reminder. So let's say that the likelihood, L, I'm just going to represent it as L of this, it's going to take, this is a bracket, in that bracket it's a feature, because likelihood is technically called a likelihood function, so it's also a function, and hence we're representing it in this way. This, let's just say that it has some value that takes on, I don't know, like 0.81. And now let's write the likelihood for some other model over here, this green model, say L of feature. And let's say that this is going to be 3.28. And this third model up here, well, let's say that this is going to be some 0.19, right? So which of these has the higher likelihood? That is the better fit to the data. And in this case, because this green model has the highest likelihood value, it is going to be the best fit to the data itself. And so whatever model we're trying to do, we would rather have this green model over, for example, the red model or the blue model. And that's kind of the overall concept of like why likelihood is so important in machine learning. But to get from let's say that we're at the red model and we want to go towards the green model, we can't just immediately just like correct such a huge degree. And typically we do this learning process of iteratively just changing the model ever so slightly such that, well, the model fit to the data improves over time. And we eventually get the best fit. And because, however, though, well, you typically would want to say, well, just keep computing the likelihood of possible models. We don't do that in practice because this likelihood itself as a function is kind of difficult and more abstract to even compute. And we would quantify this, in fact, in terms of a machine learning loss function. And we're going to be talking about that next, because in order to understand how exactly likelihood is used in practice as well, you need another concept of mathematics, and that is the very fun concept of calculus. So let me again start by motivating this example with the same kind of linear regression graph that I drew in the previous slide, so that it's here. It's not exactly the same as the previous example, but I hope this will still do. Now let's say that we have a current model, that looks something like this. And now from this, we want to say that, let's say that there's two potential places from now that we could change this model slightly to. We could either change it to this, which is a little close, trying to draw it close, or we could switch it to this green model. And now, let's actually see what's influencing our decision here. So I'm going to draw another graph over here that is going to quantify the loss function. So this loss function will typically have the coefficient as the input and the loss itself as the output, or the y-axis. And let's say that this unknown loss function looks something like this. Now, you can think of like, how is loss even related to like the likelihood situation that we came up with before? Well, you can think that like if a model has a higher likelihood and a better fit to the data itself, it will have a higher likelihood function value, and that'll be inversely proportional to this loss. And you can actually use calculus behind the scenes in order to derive that relationship. Now that's just one application of calculus. But now in this other application where, we have this very neat quantifiable loss function, we can take this red line and compute the loss and say that it falls somewhere over here, right? Let's say that if, potentially if you compute this loss by increasing the value of the coefficient, you might get some loss that's up here. But let's say that what if you decrease the coefficient a little, and you would be getting some loss that might be over here instead. So that's like the green line. Well, the way that you would look at this is, you obviously want to go towards the green line because it has a lower loss and thus a higher likelihood value. Now, whether you go in the direction of green or towards the blue, you would try to make some tangents to these points. And these tangents will be used to make decisions. But, to determine tangents themselves, you typically do that with differentiation. And differentiation is calculus. And so, incrementally, to determine whether or not this red line, which is our current state of the model, should go towards the green or the blue, you foundationally need some calculus to do this. And eventually, if you do this iteratively over time, you will get the better and better model. And once you get that better model, you can then use this for making inferences in practice. I hope that now you better understand how and why these 6 mathematical concepts are so useful in machine learning. We'll now take a little bit of a step away from the theory and now into a practical application at scale using Dataiku. In the real world, you need to wrangle data, you need to visualize it, and potentially solve problems, and run tests in an automated fashion. And in the industry, this needs to be done at scale. Now, one nice tool to solve these problems end-to-end is with Dataiku. They provide an end-to-end solution for your data needs. So, for example, let's say that you wanted to know ahead of time if a flight would be delayed or not. Now, for this real problem, Dataiku shows us how to ingest the data from different sources, prepare the data, collect features, and then eventually create a model and make predictions about new flights. You can also visualize every step of this problem with really slick dashboard solutions too. So for example, we can start by uploading a CSV of flights to make predictions on, that is whether the flight would be delayed or not. And then at the top of the dashboard, you can see like predictions for each flight on whether or not they will be delayed, with a column of either 0 or 1, depending on no delay or delay as the prediction. And you can also create some really stunning visuals of flight paths or any other bars and charts and choropleths as you see fit or find insightful in general. On top of that, Dataiku has a comprehensive documentation on how you can configure your projects with specific machine learning algorithms, so it's definitely worth checking out. So to wrap up, let's just summarize like what we did here. We came up with 6 very theoretical mathematical concepts that are super important to understand machine learning under the hood. We then tried to tie this into some practical application in the industry at scale and seeing how it actually works with Dataiku. So I hope that this video was super useful, and I wish you good luck on your data science journey.